This webcast discusses power. Power is the rate of doing work. It measures how fast work is done. So in equation form, power equals the amount of work that's been done divided by the amount of time that it took to do that work. In other words, it equals the work divided by delta T. So a couple of examples. If you walk up a set of stairs, you have done work that equals the change in your gravitational potential energy. If you were to run up that same flight of stairs, you do the same amount of work, but you do it in less time. So it takes more power to run up the stairs than it does to walk up the stairs. You're accomplishing the same amount of work, but when you do it in less time, you're doing it with more power. Also, what about a car? A car that's very powerful can accelerate, can change its kinetic energy in a shorter amount of time. So a powerful car, a more powerful car, would take less time, let's say, to accelerate from 30 to 70 miles an hour. The standard unit of power is the watt, and 1 watt is 1 joule per second, right? Power is work divided by the time that it took to do the work. Work is measured in joules, time is measured in seconds. So 1 watt is 1 joule per second. Let's go work a few problems that involve the concept of power. So I'm in worksheet 6G, and I've scrolled down to some of the problems that deal with power. So first, let's look at number 1. We've got a tugboat, and it's applying a force of 3.5 times 10 to the 8th newtons. It's moving a cargo ship 500 meters in 20 minutes, and it's asking for the power of this tugboat. Well, we've just learned that power equals the work that's being done divided by the amount of time that it takes to do that work. In this particular case, they're giving me a force and the displacement, and so I'm going to calculate the work as the force times the delta x. And so the work is 3.5 times 10 to the 8th newtons multiplied by the displacement of 500 meters. Now I've got an issue here. They gave me the time in minutes, and you know the standard unit for time is seconds. So I know that every minute has 60 seconds in it. So this is 1200 seconds. 20 minutes times 1 minute, or 60 seconds per minute. Okay. And so this is going to give me 1.75 times 10 to the 11th joules, and that's done in 1200 seconds. And so that's 1.458 times 10 to the 8th watts. In number 2, we've got Jill pulling a pail out of a well, and so she's lifting the bucket vertically straight up at a constant speed. And she lifts it 10 meters, it says, at a constant speed. And so we want to know what power is required to complete this task in 5 seconds. So the pail is initially not moving, so it's at rest. And here at position B, it's at rest again, but it's 10 meters higher. So if I consider the system that includes that pail and the earth, initially the pail really has no energy. I'll say it's at a height of 0 initially. But at the end, it's at rest still, but it's higher. And so now it has gravitational potential energy that it did not have at position A. That energy is there because Jill has done work on the pail by applying a force. And so the work that she's done has caused a change in the gravitational potential energy of the pail. And we'd like to know the power. And so in order to find the power, I first have to find the work. So the work is that change in the gravitational energy, which is the mass times g times the height. It's a 12 kilogram pail. 9.8 meters per second squared is the g, and the h is 10 meters. And so the work is 1176 joules. The power is that amount of work divided by the time that it takes to do the work. And so we've got 1176 joules of work, and they're asking for the power to do that in 5 seconds. And so that would be 235.2 watts of power required to lift that pail that far in 5 seconds. Let's go on and do number 5 here. So here we've got a roller coaster, and initially the cars on this roller coaster are at 10 meters high, and they're not moving. And at position B, they are at a height of 60 meters at the top of a hill and not moving. So we're talking about the trains and the earth here. And so let's see here. So we're not considering like the engine. The engine is doing work on these trains. Okay, so at the beginning, there is some amount of gravitational potential energy because they are 10 meters above the ground. At position B, though, that gravitational potential energy has increased quite a bit. And the difference in the gravitational potential energy at position A and position B is caused because the engine is doing work on the trains by applying a force that lifts the train up. Okay? So the conservation equation here is going to be that the gravitational potential energy at A plus the work that was done on the train equals the gravitational potential energy at B. Okay, so let's see here. So I have the mg height at A plus the work equals the mg height at B. And so the work is going to equal the mg height at B minus the mg height at A. Let's see if we've, and I can actually factor out mg. And let's plug in now. So the mass of this train is 2,500 kilograms. G is 9.8. And then the height at B is 60 meters. The height at A is 10 meters. So that work is 1,225,000 joules. The power is that work that was done divided by the time that it took to do the work. So that's that amount of work that we just calculated. And they said that this happens in 45 seconds. And so I get 27,222 watts. That is the power of that motor that lifted that train. Let's do one more here. So in number 6, we have an elevator. It begins at rest on the ground. So at rest, and the height is 0. And after 30 seconds, the velocity is 1.8 meters per second, and the height is 4 meters. So it had no gravitational potential energy at the beginning, no kinetic energy at the beginning, because it's on the ground, it's at rest. But at position B, there's both. We have some gravitational potential energy, we also have kinetic energy. And that energy that we see in the system that has the elevator and the earth came from work that was done on the elevator. The motor caused the elevator to be pulled up, and so it added energy to the system that had the elevator in it. So the work that was done on the elevator equals the changes we see in the gravitational energy and the kinetic energy. So let's find what that is. Gravitational potential energy I can calculate as mgh. Kinetic energy I can calculate as 1/2 the mass times the square of the velocity. As I plug in, I want to make sure that all of my units are in standard units. So the mass is 900 kilograms. The height is 4 meters. 900 kilograms again. And let's see, it's moving at a velocity of 1.8 meters per second, and I want to square that velocity. Okay? So the work that was done is 36,738 joules. To find the power, I take that amount of work and I divide by the amount of time that it took to do the work. Here it says that it took 30 seconds. And so that motor must have been using 1,224.6 watts.